code. So let me just start recording. So here what we are going to do is that maybe let me create for myself a little bit more room so that we can solve this problem. Okay, so are we all able to see? Are we all there?
Yes, sir.
All right, so we are talking about that question. We are saying that the drawing looks like this. So we have a line of charge. We have a line of charge. Okay, so it has got charge everywhere. Okay, and of course we are told that the length of this line is L. So there's something that I'm going to do. We are told that can we find, you see, its axis is in this direction. You pardon my drawing, it may not be very, very good. So my axis is at that particular point. Now I must construct a coordinate system. The point, this is along the x-axis. So this is along the x-axis. It becomes very important for us to construct a coordinate system. Okay, and then what is the origin? The origin, I'll choose the origin to be at the point where I want to calculate the electric field. So I've chosen my origin at the point P. So this is the point P where I want to calculate the electric field. So it means that at this particular point P, this is the point. Since it's the origin, I'll say x is equal to 0 at that particular point. Okay, x is equal to 0 at that particular point. Now, according to the question, if you read the question very well, what did they say? What is the distance from the point P where you want to calculate the electric field to the end of the rod? What does the question say? What was the distance there?
Distance A.
The distance was A. So the length there is A. Okay, the A is the distance from the point where I've taken my origin to the end of this rod. So you can see at this particular point, what is your x if you want? At that particular point, your x is equal to A. Are we all together? At that particular point, your x is equal to A because x is equal to 0 is at the point where you want to calculate the electric field. Okay? And then the next thing, okay, so the next thing that we want to do is this to assign. So what do you think is this point? What do you think is this point here? I'll say this point x is equal to what? At the end of the rod, x will be equal to what? Remember, the length of the rod is L. So from here up to there, it is L. So then, if that is the case, at this point, x is equal to what?
L plus A.
Yes, so L, remember we are starting from here. This is x is equal to 0. So there is A, okay, and then there's also L. So at this point, we can say that this x is A plus L. Okay, Madam Petronella, thank you very much. We are doing very fine. And I just wish that everyone else could be able to contribute so that we know that we are moving together. Okay, so now hello? So what we are going to do is that we are going to assume that this rod here is made up of an infinite number of small elements of charge. And then let us just consider only one of those elements. Let us say this element is just somewhere here. We just consider one small element of charge. And then we say, since this is along the x-axis, we'll say that it has got a length of dx, and then it also has a charge of dq. Okay, it has a length of dx, this small contribution here. Okay, and then it has a charge of dq. And of course, you know that the distance from here up to here, let us just denote it as the x. Let us just denote it as x, and our x will be a variable. We can take this element at any point along this line, but the lowest that we can take it is at this point. What is this point? X is equal to a. Okay, so welcome back. Okay, welcome back, class. Hello? Are we there?
Yes, sir.
Okay, I'm sorry that I had the network challenges. Okay, so nevertheless, let us proceed. These are some of the challenges that we expect, the downside of this system. Okay, so I think this is just another diagram that I've drawn. Okay, so as you can see here, this is the road. It has got charge everywhere, as I had explained earlier. Okay, so we decided to construct a coordinate system. The coordinate system, we constructed it in such a way that so we constructed it in such a way that the origin coincided with the point where we want to calculate the electric field. And then since from the question, we have been told that the distance from one end of the road to the point where you want to calculate the electric field is A. So this point, we can say X is equal to A. And then at this point, the other end of the road, the X is equal to A plus L. Okay, and then as I had indicated earlier, you imagine that this road here is made up of an infinite number of small elements, each of length dx and containing the charge dq. So I have drawn, and then of course I say the last point I tried to make was that this element here, you have taken it at a distance x. You can see x is a variable. The smallest value that it can assume is when you take this element right at the at this end of the road where x is equal to a. So we say that the lower limit of x is x is equal to a, and the furthest point where you can take this element is right at this other end where x, as you can see, is equal to a plus L. Remember, the length of this road is L. So we are saying that the distance from here up to here is nothing but L. So L is that distance there. Okay, so we have now set up the problem. We have now set up the problem, and then we have now to use that procedure that we had outlined before. So we say that at that point there, the dE, the element of the electric field, the contribution of the electric field for this element here that has got a charge of dq is nothing. We are going to denote it by dE. So we are saying that the dE will just be equal to, remember from the law, there is k there, and then there is dq, and then there is what? And then there will be r squared. For now, we'll just say r squared. Okay, but we must bear in mind that r is nothing but the distance from this element up to the point where we want to calculate the electric field. So now let us try to see, what do you think is r in this case? Let us be together. What do you think is r in this case? I want someone else apart from Madam Petronella. We all need to be participating in the class. So what is r in this case? What is r in terms of the variables that have been given? No?
L.
R is equal to L. Okay, are you sure? Remember, R is the distance from the charge to the point of interest where you want to calculate the electric field. So in this case, R will be equal to what? R in this case is just equal to X. Remember, we had said that the distance from here, the distance from here to here is nothing but X. The same distance from here to here. And so R is equal to X, and X is basically our variable. So in this case, R is equal to X. So we are saying that dE dE will just be given by K, and then dQ over X squared. All right, I'll not talk about the direction for now. I'm just looking at the magnitude. Just consider the magnitude. Okay, so now the next thing is that, remember what we had said was that we have now to consider this dQ. Express this dQ in terms of an appropriate charge density. So looking at this distribution, is it a linear distribution, is it a surface distribution, or is it a volume distribution? Looking at this distribution.
It's a linear distribution.
It's a linear distribution. So linear distribution, it means that the associated charge density is lambda. So lambda will be equal to, in this case, remember this, the lambda within this small element here is the length, is the charge per unit length. So this can just be written as dQ over dx. And then here we are interested in this dQ so that we can substitute it into that equation. So this implies that the dQ will just be given by lambda times the dx. Okay, hope we are all moving together. And then so now we
Yes, sir.
have to substitute this expression here. We now have to substitute it here. So then the dE, remember, dE is just the contribution of the electric field due to this small element here. So the dE will just be given by the K. Remember this K that is already there. And then this dQ, I'm going to write it in terms of the linear charge density. So it gives me dx and then over the x squared. So we are making progress there. Okay, so at the end of the day, now we have to, this is just the contribution due to this small element. So now, ultimately, what I want is to add the contributions of all the other elements from x is equal to a up to x is equal to a plus l. Okay, so that in mathematics we call that integration. It means that I have to integrate on all the contributions between those limits. I have to integrate all the contributions between those limits. So in mathematics, as a matter of principle, before you integrate, in order for you to integrate, you must only have one variable. All the other parameters must be constant. Okay, that variable is what you call the variable of integration. So let us check out this formula and see whether we only have one variable. So you see, this k here is a constant. The constant, know that its value is 1 over 4 pi epsilon naught. And then this lambda here is the linear charge density. Now from the question, if you look at the question carefully, you have been told that the charge density is uniform. So since the charge density is uniform, this guy also is a constant. So you can see that the only variable that we remain with is the x. And since we only have one variable, then we can integrate. Then we are good to integrate. So this implies that you integrate on the left-hand side, dE will be equal to, and then these, since these are constants, you can actually pull them out of the integral. Then you have that, and then you integrate this. Here you just have dx over x squared. Okay. All right. So up to that point, maybe let me get your input. Are we all happy up to that point? Are we all happy up to that point before we proceed? Or have I lost someone?
No, sir.
We are together. Okay. So now, if you integrate on the left-hand side, it means that what will be the integral of the left-hand side? What will be the integral? It will just be e. Okay, it will just be e. Okay, and then on the right-hand side, you see I have this. These are constants, so they will not. I'll not worry about them in the integration. So the k and the lambda, and then now this integral. How do you evaluate this integral here? And before we talk about the evaluation of the integral, let us talk about the limits, because this is a definite integral, so it must have limits. So this integral, what will be there? Its lowest value. I think we have already explained that. The lowest value of x is x is equal to a, because that is where the rod, that is where the charge is starting from. All this space has got no charge. The charge is starting from here. So the lower limit will be a. It is the lowest value of this element that you can get. In the same vein, the upper limit here will be a plus L. So those are the limits of the integral. Okay, so having said that, now how do you integrate this? How do you evaluate this integral? Which method are we going to use? Which method are we going to use? Which method are we going to use? Hello?
Substitution.
Substitution. Okay, so now let us make a deal. I think if you guys, you don't want me to ask questions, if you don't want me to be asking you the questions, okay? If only one person is going to be answering, then I'm also going to boycott. And the way that I'm going to boycott is that I'm just going to teach. And then I'm not going to ask you anything until I finish. That will be very easy for me. I'll assume that it is okay. So let us make that deal. If there's only one person who is willing to be participating, then I'll assume that the others are very much comfortable, and I'll just go straight without asking. Okay? Do we want to go that way?
No, sir.
But why? Why?
The process of unmuting. I'm sure she's too quick to unmute. The process of unmuting. I'm sure she's just too quick to unmute.
She's quick to unmute. No, but you can still raise hands. You know how to raise hands and so on. So I will know that this person is, someone is ready to speak. Then I will choose who can contribute at that particular time. Okay.
So some of us need stripping.
Okay, so let us go ahead. So I think someone suggested that we can use substitution. Yes, Mr. Kafwembe. Mr. Kafwembe, what method do you think we can use? Did I see the hand? Mr. Kafwembe? Mr. Mcheka? Hello, okay, as we are waiting. Yeah?
We can use the first principle.
We can use the first principle. What is what is the first principle? What is the first principle?
Where we are going to differentiate dx over x squared. In this case, we're going to say 1 over x, which will be the negative. Then we distribute the limits. In this case, we are going to say the q over the constant outside, open brackets, the negative 1 over x, close brackets, L plus a, upper limit over a, and down on the bottom there we put a.
Okay. All right. So that's actually the correct, that's the best method that we can use here. Sometimes it is called this polynomial integration. Sometimes it's called polynomial integration because you know this, you can consider it to be a polynomial. Okay, so how we are going to do it, basically as Mr. Mcheka has already explained, is that if you want, you can squeeze in another step where you can write this as you write it a to a plus L, and then you say this x, you express it in the index form as such as the x minus 2, and then you just say the x. you know this 1 over x squared, you can also express it as the x to the power minus 2. And then from there, we can now use the polynomial kind of integration. Now, the polynomial kind of integration is where what you do is that you just add 1 to the power here. You just add 1 to the power and you divide by that number that you have found. Okay? So that is basically the method that we are going to use. Just allow me to rub this part so that I create space. I rub this part. Okay. So if we perform that kind of integration, then you find that we have E, which is the electric field. Then the electric field at that point P, electric field at that point P will be given by this K here times the lambda, which is the charge density. And then this X, if I add a 1, what does it become? It gives me X to the power what? Negative 1. Because you know, minus 2 plus 1 gives me a minus 1. And then over, the answer that I found here is minus 1. Okay, so the electric field then will just be, you know, anything divided by 1, so it will just be equal to minus K and that and over X. And remember that we also have the limits to deal with. We have the limit A, then A plus L. Okay, here we have the limit A, then A plus L. Okay, so at that particular point, I will just now leave it for you to finish it off because I think I've done much of the work. So if you do that, you know, you just now substitute the limit. You substitute the limit there, then what you get is, you know, this okay, let me just help you. You have this, and then what you have will be 1 over x plus L. Sorry, 1 okay, 1 over A plus L, and then minus 1 over A. Basically, I'm sure all of you understand what I've just done is that I'm substituting the limit. I take the upper limit, I place it here. I just leave this constant. If I substitute, I plug in the limit, then I get this. This is the upper limit minus. Now I come to the lower limit. My variable here is 1 over x. I put it there, then I have that. Okay, and that is that. The next thing you just need is to do a last step, very last step. Okay, and this step is just for me to distribute this negative that is here. Distribute the negative, then I have E, the electric field will be K, that, and then this will now be 1 over A minus 1 over A plus L. Okay, and then I also know that K is just nothing but 1 over 4 pi epsilon naught. I then come to my final expression where I have this lambda. Okay, maybe before I write the final expression, let me do something else. I know K is equal to that. And what is this? This is the linear charge density. Okay, the linear charge density, since it is uniform, it can also be expressed as the total charge over the length by definition. The linear charge density is the charge per unit length. So it can be expressed in that way. So if I substitute these two things there, then the expression for the electric field that I get will simply be, Q over 4 pi epsilon naught L, and then I have 1 over A plus minus 1 over A plus L. And that now becomes the expression that I'm looking for. Okay, so this is now what we are saying, that this is my symbolic answer. It is, in case I know the length of the rod, the length of the rod, I can also know the charge, the total charge that is on that rod. And I also know A, which is the distance from one end of the rod to the point where I want to calculate the electric field. Then I can actually calculate the electric field at that particular point. Okay, so let me pause here for questions. Any questions? Any questions?
It's clear, sir.
Okay, it is very clear. Thank you very much. This lesson is being recorded. So if you think that you lagged a little bit and you would want to just replay somewhere, I think it will be accessible to you at the end of the lecture. Okay, so now at this point, let me go back. Let us go back to the slide. Okay, so what we have done so far, is I think we have actually derived this expression. We have derived this expression up to here. Okay, so we have derived this expression together. Okay, if you want, you can, I'll now leave it for you as a very simple exercise. You see that you can actually factor out this A, which is common. If you factor out this A, which is common, you can actually simplify that expression to that. I'll leave that for you as a simple exercise in your spare time. Okay? And from there, there's something that that we need to do. So let us consider this expression. What does this expression become? What does this expression become in the limit where A is greater than 0? In physics, when we obtain an expression, the other thing that we want to do is to look at that expression in a certain limit, and be able to see whether that expression is making sense. Okay, so now, if A is much greater than L, what does it mean? L, remember, L is the length of this rod, and A is this distance. So if A is much greater, it means that you are moving further and further away from this rod. And as you move away from this rod, then this rod, you start looking, when you look at it, you start viewing it as a point charge. As you move further and further away from this charge, then this charge will start appearing to you as a point charge. So in this limit, if you look at this, work out this expression, if it is correct, it must give you the expression for, a point charge. So let us try that together. So if in this expression, if A is much greater than L, if A is much greater than L, from this expression, it means that this L is almost equal to 0. Because it is more like we are adding a very big number, like 1 million, and then you add 1. So whatever answer that you find, it will be almost the same as 1 million. Okay, so it means that this L is much less than A, and it is negligible. So you see that in that limit, in this limit, then you find that the expression will just be equal to E will be the same as Q over 4 pi epsilon naught. And then since this is almost 0, when you multiply that and that, then you're going to have A squared. Are we together? So therefore, this E can just be written as, remember, 1 over 4 pi epsilon naught is just nothing but k. So it can be written as k q over a squared. And then a is basically the distance from this point charge to the place where you want. So as you can see, this expression is simply the expression for a point charge, the electric field due to a point charge at a distance a. So this indicates to us that this expression that we found is correct because it is giving us a reasonable answer in that particular limit where this a is much greater than L. Okay, any questions before we proceed? Any questions? Okay, so there are no questions, so we proceed. Now let us look at another concept that is very, very important as we discuss the electric field, and this is the concept of the electric field lines. Okay, so we can visualize, this is just basically helpful for us to visualize what is happening. Okay, so we can visualize that in all the space around a charge, there is a quantity that is called there are actually electric field lines. And the properties of these field lines, the first one is that the electric field vector is tangent to the electric field line at any given point. So for instance, look at this point here, look at this, look at this point here. The electric field is tangent to the field line. At this particular point, the electric field is tangent to the field line. So this is one of the properties or when drawing the field lines. Okay. The next property is that the number of lines per unit area through a surface perpendicular to the line is proportional to the electric field. Now, what this one means, you know, is proportional to the magnitude of the electric field. So in short, we are saying that the density of the field line, okay, the density of the field lines is actually proportional to the electric field. So where you have more field lines, more field lines that are closely spaced together, then the electric field is bigger there. For instance, you can see in this diagram, for example, if I was to consider this point here, this point, let me call it point A, and I consider another point here, let me call it point B. Between point A and point B, where do you think the electric field lines are more densely, more closely packed? Is it on A or on B? Where do you think that the electric field lines are more close together?
On A.
On A, you can see that on surface A, there are more electric field per unit area than at point B. So this shows us that the interpretation to this is that the electric field at point A is greater than the electric field at point B. Okay, so the next thing, maybe I can also illustrate it here. You see, if you draw a circle at this particular point, draw a circle, and you draw another circle at this particular point, you can see that the number of lines as you go outwards, the density of the lines becomes less, means that the electric field is decreasing. Okay, the other point that I want to mention is that these electric field lines, they always originate from the positive charge and they terminate into the negative charge. They always originate from the positive charge and they terminate into the negative charge. And hence, we say that the positive charge is the source because that is where they are originating. And then the negative charge, we say it is the sink because that is where they are terminating. So all the time you must understand the electric field. Whenever you see an electric field, whenever you see electric field lines, you must know that there is a charge somewhere. And the direction of the electric field lines will determine the nature, the type or the sign of the charge. Okay, so I think this one I've already explained it implicitly. I've said that this is just what I was trying to explain, that the electric field lines, they begin from the positive charge and then they terminate on the negative charge. Okay. In the excess of one type of charge, some lines will begin and end infinitely far away. So what does that mean? For instance, you can see here, these electric field lines are originating from the positive charge. They are terminating into the negative charge. But then look at these. These are the ones that this statement is referring to. Say that in the case of an excess of one type of charge, some lines will begin or end infinitely far away from the charge, as you can see from there. Okay, so what is the other thing that I want to highlight from this slide? The number of lines drawn leaving a positive charge or approaching a negative charge is proportional to the magnitude of the charge. Okay, so yeah, that is just basically one of the conventions that is used. If, for instance, you say that you have the charge 1 is equal to 6 microcoulombs, and then charge 2 is 20 microcoulombs, then the number of field lines that are originating from charge 1 will be less than the number of field lines that are originating from charge 2, because the number of lines are proportional to the magnitude. Okay, if you feel that you have any question, feel free, please, to just come in, and then you stop me. So I have a question here. Rank the magnitudes of the electric field at points A, B, and C. It's a very, very simple question. Maybe let us try to see if we can do it. Okay, we do it only. Okay, maybe let us just discuss it because we are remaining with very little time. Okay, so what do you think? How do you rank based on what we have discussed in the previous slide? How do you rank the electric field, magnitude of the electric field at point A, B, and C? The class, to the lecture, what we said, the principle that we are applying in this question is that the density of the electric field lines represents the magnitude of the electric field. The density represents the magnitude of the electric field. Now, if you can see point A, around point A, okay, the electric field lines are more densely populated, okay, than point B. And then if you compare point B to point C, at point C, actually there are no electric field lines, meaning that the electric field is actually 0. Okay, so you can see that the highest, the greatest is A, followed by B, followed by C. The principle that we are using is just looking at the electric field lines, using the concept that the density of the electric field lines represent the magnitude of the electric field, and hence I think that is why Mr. Kawita opted for this answer, which is the correct one. Okay, so now let us look at how motion of a charged particle in an electric field. Okay, so here you can see in this diagram we have the source of particles. Say this box is where the charged particles such as electrodes are coming, and then they are made to pass through. They are made to pass through an electric field. Okay, so in order to illustrate. Hello. 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 Are you able to get me? Class?
Sir, we are able to get you.
Okay, so I think let me just go to the whiteboard. I want to share the whiteboard because I want to do some, I want to illustrate something there. Okay, so imagine that you have this Okay, let us say that this plate has got a negative charge on it, and this plate has got a positive charge on it. Okay, in between here, it is just empty space. And let us say that here you have electrons. Here you have electrons, an electron that is moving in this direction. Okay, this electron here on this part, you have a screen. I'll explain what the role of the screen in this particular case. Now, if you have this plate that is positively charged and this plate that is negatively charged, what do you expect to have in this region in between? What do you expect to have?
Negative.
What do you expect
A
to
deflection.
have? Okay,
A
no,
deflection.
no, don't go ahead. I'm just saying that if you have a negatively charged plate, a positively charged plate here, and a negatively charged plate here, what do you expect to find in this region here? What do you expect to find?
Magnetic field lines.
Field of electric field.
You expect to have
Field.
an electric field. You expect to have an electric field which can be represented by electric field lines. And what will be the direction of that electric field? Remember, the source is the positive charge, the sink is the negative charge. So in short, the electric field is from positive to negative. So the direction of the electric field is in this way. So this is the electric field. Now, what we are saying is that if you have an electron, let us say you have an electron, it is coming in this direction, and then it passes through a region where there is an electric field. What will be the behavior of this electron? That is what we are saying. Okay, so the behavior of this electron, as the electron is passing, you know that the electron is negatively charged. So as the electron will be passing through this region, it will be repelled by this because they are like charges, so it will be repelled by this, but then it will be attracted by that plate. So in short, at any given point, there will be a force acting on it, and therefore, maybe just let me just draw it a little bit properly. I want to draw it here. Okay, so you have the electron, it is moving here in this region. So as it is moving, it will have a path such as this one. Okay, it will have a path such as this one. So we say that it will be deflected. It will not, as it passes through the electric field, it will not continue moving in a straight line, but then it will be deflected. Why is it going to be deflected? Because of the force that is being exerted on it by the negative plate as well as by the positive plate. The positive plate is trying to attract it, the negative plate is trying to repel it, but then there is also the motion, the force due to the motion, so as a result, it has a deflection. Okay, so now let us look at this, what is happening here a little bit more closely. Okay, now I think I talked about the screen. There is a screen there. Now this screen is made up in such a way that it can detect the charge. Where the charge lands, it leaves a spot. So you can see that if you do this setup, you're going to see that you're going to see a lot of spots on the upper part, indicating that the electrons have been deflected. Okay, so now let us look at the forces at play. What forces can you think of that are acting here? What forces can you think of that are acting here? That are acting on the electron as it passes through this region? Huh?
Repulsion.
The repulsion. So how can we understand that? The repulsion, it is an electrostatic force, right? So we say that there is this force that is acting. Force is equal to the magnitude of the electron times the electric field. Correct? Do you remember this equation? This equation is coming from the definition of electric field. Recall, electric field was defined as the force per unit charge. You remember this, eh? Electric field was defined as the force per unit charge. Now, in this case, the charge here is the electron. So I'm going to remove this. I'm going to remove this, and then I put there the electron. And then if you make the force subject of the formula, then you come up with this equation. Okay, so what is the other? So what is the other force? What is the other force that is acting on the electron?
Attraction.
What?
Attractive force.
The attractive force. Yes, this force is what we are calling it the Coulomb force. This is the Coulomb force that I've written, both repulsion and attraction. What other forces can I think of? Huh?
Gravity.
Huh? Oh, sorry. I think I should share. What I want to share is okay. What I want to share is this: gravity is acting on it. Okay. Yes. All right. Maybe let me help you. Okay, let me help you. You know that this force here, this force that is here, I don't know, I've lost my... Okay, so I think we have already made a bit of progress so far. What we are saying is that there is this force. There is this force that is acting due to the Coulomb force. We say that this force, we have already established that it is E times E. This is the electronic charge. This is the electric field. But this force here can be written according to Newton's law. It can be written as the mass times the acceleration. Okay, so if you equate these two, then you are saying that this EE must be equal to the mass times the acceleration. Okay, and if you make acceleration the subject of the formula, then what you just get is the E times the E over the what? Over the mass. So this is the expression that you use when you have a charged particle such as an electron that is moving within an electric field E. It is accelerated, and the magnitude of the acceleration is given by this formula. So if you know the magnitude of the charge, you also know the electric field, you also know its mass, then you can actually find the acceleration. Okay, so that is basically what we have here. Okay, the next thing that we want to find is that what is the behavior of a dipole? Remember, we had talked about a dipole. What is the behavior of a dipole when it is placed in an electric field? So in this diagram here, you can see I have a dipole. Remember, a dipole is just a system of two charges, negative and positive, that are separated by a certain distance. So if you take this dipole and then you place it in the electric field, then how does it behave? This is the interest of this slide. Okay. So if I would again want to use to illustrate this point via the whiteboard. Okay. Okay, so we are now saying that if you have a dipole is something that looks like this. Okay, this is the negative charge, and then this is the positive charge, and then we are saying that let us consider this is the axis. Maybe we can call it the x-axis if you want. And then we choose the x-axis in such a way that it divides this dipole into two. If the distance of the dipole is, it means that the distance from here to there is d over 2. The distance from here to here is also d over 2, such that the length of the dipole is d. I hope that we are making sense together. So the distance from here up to here is d over 2. The distance from here to here is d over 2. And so that the total distance here is d. Okay? And then let us say that the angle that is here is theta. The angle that is here is theta. Okay. Maybe just allow me to rub this. I start all over again, so that maybe it will become clearer. Let me rub here. So let me say initially. Okay, so have you seen what is happening? What is happening is that we have this dipole. It has got a positive charge and it also has a negative charge. And this dipole, you know, it is vertically oriented like this initially, and then it is placed in an electric field. Okay, so now what will happen to this dipole? What will happen to this dipole? You know, since this is a positive charge, what do you think will happen? There's an electric field. This positive charge is in an electric field. It means that it is going to experience a force in the direction. So there will be a force in that direction. What will be the magnitude of this force? It will be Q times E, what we just learned not so long ago. So the force will be pushing in on it since it's a positive charge. And then what will happen to this negative charge? There will be a force on it, but then this force will be in the opposite direction since it is a negative charge. The magnitude of this force is the same. It will be equal to Q times E. Are we together? So this situation, because there are two forces that are acting on this dipole in opposite direction, we are going to have a final situation that looks like this. There will be a rotation. You see that it will rotate because you have a force acting in this direction and another force acting in this direction. Then this dipole will rotate, and its final configuration will look something like this. Its final configuration will look something like that. Okay, so this is the electric field, and then this, of course, this still remains your d over 2, and then that remains your d over 2. This is the origin, And then because of these forces that are acting, there's a force that is acting on this direction. There's also a force that is acting in this direction. And this dipole will be rotated. It will be rotated through okay. Okay, so it will be rotated through a certain angle. I'm trying to draw the normal here. So it will be rotated through this angle. Okay, so I just repeat, just for the sake of clarity, that initially you have a dipole that is oriented in this manner within the electric field. The electric field is pointed to the right. So because of the forces that are exerted on the negative and on the positive and the negative charges in a dipole, this dipole is going to rotate. It is going to rotate such that its final configuration will look like this. This is the positive charge. Okay, and then with respect to the vertical, it would have rotated through an angle of theta. So this is theta here. Are we together? So now in first year, you may have learned that anything that has been rotated, we can talk about the torque or the turning effect. What is the turning effect of this dipole when it is placed in this, within this electric field? What is its turning effect? What is its moment, or what is its torque? So remember from your first year, you said the torque is equal to what? Torque was equal to what? Huh? Do you remember that formula for torque? The torque is basically the product of the force and the lever arm. The torque is the product of the force and the lever arm. Now I need to, the force that is acting is this. For instance, the force that is acting on this is that. Okay. And then what is meant by the lever arm? The lever arm is basically the distance from the pivot to the line of action of the force. The distance from the pivot to the line of action of the force. So you see that the force is acting at this particular point. So its line of action. So this here is what is called the lever arm. This here is what is called the lever arm. So as we had discussed already, you know that the distance from here to here is the d over 2. It's the same as this here, d over 2, the distance from here. So if you want to find the distance, this distance here, which is the lever arm, it will just be equal to d. So we say the torque is the product of the force and the lever arm. So the lever arm in this case is this distance here, which can be expressed as the d over 2 sine theta. D over 2 sine theta. Okay, so it means that this torque that is coming from the positive charge can just be written like that. In a similar way, similarly, the torque from this for the negative charge can also be written. Now you can see that this one is a minus. Okay, well, it is still a plus because it is causing a clockwise rotation. So this can also be written as the force times the lever arm, which is d over 2 sine theta. Okay, are we together there? Are we together?
Yes, sir.
All right, it seems you guys are tired. Are we tired?
No, we are not.
Huh? We are not tired. Let me just finish this calculation here. Let me just finish this calculation there, and then I'll leave you. Okay, so if you add the contributions of these two, there is this torque which is coming from the positive charge. There's also this torque that is coming from the negative charge. Then the total torque will just be equal to this torque plus this torque. Okay, and if you add this, you see they are the same terms. If you add them, you see there is FD sine theta over 2 plus FD sine theta over 2. Then you just come up with FD sine theta. You come up with FD sine theta. And from there, now what is F? What is F? We have already established that this F is just nothing but E times E. So the torque will just be given by this E times E times D and then sine theta. All right, and then I can try to rearrange this. I write it as E times D times E and then times sine theta. Why have I rearranged it? Because I want you to have a look at this. What is this? Okay, this is the product of okay, maybe since the charge we are using Q, we are not using E. So maybe let me just rub this E and I put a Q. So I'll rub everywhere where I've written E because for charge we are using Q. So let us be consistent. So we have Q here and then we'll have also Q here, then we have Q here. So now I'm interested in this. What is QD? What is QD, which is the product of the charge and the separation distance in a dipole? What is it called? It is called the dipole moment. So this torque can be written as the dipole moment and okay, the dipole moment and this E sine theta. So that is the expression that we are going to have for torque. So as long as you know the dipole moment, you also know the electric field, and then you also know the theta. Theta is the angle through which this thing has been rotated. Then you can actually find the torque. Okay, so any questions there? Any questions? I think I can now go to my, I can stop sharing the screen. I can stop sharing this screen and I think I go to my slides. So those things that we were doing, those steps, those calculations that we are doing are simply the ones that are shown there in a summary form. If you want to see all the steps, then you can go to that, to the whiteboard, and then you see how we have done it. So at that particular point, we have reached here where we said that the torque can just be given by that equation. And from your mathematics, I just want to remind you the issue of cross product. I think in vector calculus, you learned about something like dot product. The dot product of two vectors is just the magnitude of the two vectors times the sine of the angle between them. So this torque here can actually be represented in vector form just as the P cross E, where P is okay, so I'm saying that this torque can be expressed as a vector product of P and E, where E is the electric field and P is the dipole moment of this dipole that is here. Okay, so I can see that you guys are tired. I think I'll just leave you with this small homework here to just be able to show that if you put a dipole in an electric field and then that electric field tilts it or it rotates that dipole within that the angular displacement of theta, then the potential energy of the dipole will be given by this. I will give you that as an exercise so that in the next class when we meet, I think we'll start from there. Okay, so in summary, the summary of this lecture, we have learned several things. The first thing that we have learned is that the electric field is a quantity that is defined in terms of electric force. So we say that it just represents the electric force or the Coulomb force that acts on a test charge, the one that acts on a test charge. So in short, we learned about this, that the electric field is basically the force acting per unit charge. Okay, the other thing that we learned is about the electric field lines. We say that it is a very good way of visualizing the electric field in terms of magnitude and direction. The direction is represented by the arrows, and the magnitude is represented by the density of the field line. Okay, so the other thing that came out was the electric field. I think we calculated the electric field due to a point charge. We said that the formula for the electric field due to a point charge at a point which is a distance of r away from the charge is given by that. I like writing this equation just like electric field is just equal to K and then times Q over R squared, where K is 1 over 4 pi epsilon naught. Okay, the other thing that we did is that we derived the electric field due to along the axis of a dipole at a point Z away from the center, and then we found this to be the electric field. All these things you must practice them because they are the things that will become very important even in your test and examination. Practice how to derive these results. Okay, the other thing that I think we also talked about continuous charge distribution, this aspect of continuous charge distribution, and we distinguished it from discrete charge distribution, which is basically made up of point charges. Okay, so we said for continuous charge distribution, the dimensions are very important, whereas for discrete charge distribution, the dimensions are negligible as viewed from a distant perspective. Okay, the other thing, of course, from this equation, we can see that the force can be given by QE, and then this led us finally into these results where we asked ourselves to say, if you place a dipole in an electric field, what will be its behavior? We say the answer was that it will rotate. It will have a turning effect. That turning effect is called a torque. And that torque can actually be given as the cross product of the dipole moment and the electric field. That is the first result that we had derived. Okay, this one. So you must practice and make sure that you are happy with the derivation of that result. It's important for you. The next result, I think, which I gave you as a homework to go and try on your own, and then we discuss in the next class where you will not be clear, is that if you place a dipole in a magnetic field, then it will have a potential energy, and this potential energy can be given by this expression. Okay, so ladies and gentlemen, for today, this is where we have to end our class until we meet next time, which will be on Monday, God willing. But for now, maybe I can invite questions, contributions, and comments before we close the class.
Yes, good afternoon.
Good afternoon, thank you.
Yeah, I've seen on the model that you've put some recurring meetings starting from tomorrow. So you've mentioned to say you are meeting on Monday.
Okay, so
meaning we're not supposed to follow what is on model.
Okay, no. I think that those meetings, I created them in a hurry because you see, it was that time when I realized that my Google email address that I had created the first meeting with, it performed. So I decided to create those meetings with using my Mlungush account. So those are, just ignore that program that has been made. I actually just wanted to make recurring meetings so that we are using the same credentials, the same login credentials, so that every time I don't have to be posting the link, because it's a recurring meeting. So what I'll do is that immediately after this class, I'll go and edit those meetings so that they are consistent with what we are going to be having. Okay.
All right. Thank you. Thank you.
Anything else?
Sir, I wanted to ask, where can we find these recorded videos?
Okay, maybe first let us do this. Any questions based on what we have learned? Any questions? Okay, so it seems there are no questions. Then I can stop this screen.